Welcome back to the Deep Dive. Great to have you with us. Today, we're doing something really essential. Think of it as a personal training session, We're focusing on sharpening your understanding of core welding principles, specifically for the CSWIP 3.1 Welding Inspector Exam. We've got some key insights here, framed as challenging questions to really test your knowledge, get you that edge or mission, go beyond just the what's, and really explore the why behind these crucial welding practices.
Exactly. And it's not just about memorizing facts for the exam. It's about building a really solid foundation in welding inspection, precision, and, deep understanding. They're just non-negotiable.
Right.
Knowing these details is absolutely key for certification, yes, but more importantly, for safety, for quality out there in the real world. We're here to help connect those dots for you.
All right, then. Let's jump right in. First challenge question. This one catches people sometimes. Here it is. Which welding process is commonly used for welding aluminum and magnesium? Your options are A, submerged arc welding, or SAW, B, gas tungsten arc welding, that's GTW or TIG, C, shielded metal arc welding, SMAW or STIC, and D, flux cored arc welding, FCW. So take a second. Think about those tricky reactive metals. Which process is the go-to? Okay, got your answer. The correct one is B, gas tungsten arc welding, G2 TIG.
Yeah, TIG. And the really critical thing to grasp here is why it's the standout choice for aluminum and magnesium. Like you said, they're sensitive metals, very reactive. TIG just offers some huge advantages here. First, you get superior arc stability, really stable.
Yeah.
Incredibly precise heat control. That's vital because, aluminum and magnesium have lower melting points. They can distort easily if you pump too much heat in too fast. And maybe the biggest factor, TIG lets you make really clean welds without flux. Flux residues can be super corrosive on aluminum and mag, causing problems down the line. Plus, for these reactive metals, that inert gas shield, usually argon, maybe helium, is absolutely, it just completely surrounds the weld pool, stopping oxygen getting in. Prevents that instant oxidation that would mess everything up.
Right. That oxide layer forms almost instantly otherwise, doesn't it?
Instantly. And it's tough. So TIG prevents that. Now, if you think about the other options, SAW. Too much heat, deep penetration, relies on flux. Not good. SMAW quota, less control, slag formation. Again, not ideal. And FCAW uses flux inside the wire, so you still have potential flux issues. TIG avoids all that for these specific materials.
That makes perfect sense. And you often see those really clean, almost beautiful welds on aluminum parts, bike frames, things like that. It's usually TIG, right? It just looks clean.
It does. It speaks to the quality possible with the process.
But, okay, if a TIG weld looks clean on aluminum, what subtle signs should you, as an inspector, still be watching for? Those hidden oxide inclusions you mentioned, are there telltale signs? Oh, that's a really good question, and exactly the kind of thinking needed, because yes, they can hide. You'd be looking for very subtle things, maybe a slight change in the bead shape, the contour, or perhaps a duller spot, an area that looks less shiny, or maybe the gas coverage faltered for just a second. Sometimes, honestly, you only find them with radiography, but visually, minor inconsistencies in how the ripples flow or the bead width, that can be a clue. Even just a slightly rougher surface than you'd expect from TIG, that could suggest some contamination got in. It demands a really close look.
Meticulous is the word.
Okay, sticking with TIG's precision, let's think about defect prevention, knowing how to stop problems before they start. Next question focuses on that. In the TIG welding process, slope in, slope out capability is useful in order to. Options are A, avoid start porosity in crater pipes, B, reduce the risk of tungsten inclusions, C, stabilize the arc, D, allow more time for the filler metal to melt. So think about the very start and the very end of the weld. What are the big risks there? Got it. The answer we're looking for is A, avoid start porosity in crater pipes.
Right. And this is where those seemingly small machine settings become really important for the final quality. Slope in and slope out, they're basically just current ramping functions, managing the heat. Slope in is that gradual increase in current right at the start. If you just hit it with full power, instantly, bang, you risk porosity, little gas bubbles getting trapped, or even thermal shock. Slope in lets the weld pool establish itself nice and smoothly, and then slope out just the opposite at the end. It's a controlled, gradual decrease in current. This lets the molten pool cool and solidify slowly, completely. If you just cut the power suddenly, the center cools last and shrinks inward, often leaving a hole or a dip that's your crater pipe. And it's not just ugly, it's a weak spot, a stress riser, a place where cracks love to start. So controlling those starts and stops is crucial for the integrity of the whole weld.
Yeah, it's like easing your foot onto and off the accelerator in a car, right? Avoids jerky starts and stops. Makes a huge difference to the smoothness, or in this case, the strength. But are there times when a welder might be tempted to, Cut corners, skip or shorten the slope out to save a second or two, maybe on a production line.
Oh, absolutely. Time pressure is always a factor.
And what are the immediate signs an inspector would spot? What's the giveaway?
Well, the most obvious sign of insufficient slope out is exactly what we mentioned, the crater pipe. You'll see a distinct concave depression right at the end of the weld bead. Often, you might even see a tiny crack right in the middle of it in an exam if you see a picture of that. Your first thought should be improper slope out. And long term, that pipe is just asking for trouble. Fatigue cracks love starting there. It's a serious defect, even if it looks small.
Got it. Easy to spot, but with serious consequences. Okay, let's stick with TIG for one more. This one flips it around what defect is not typical for TIG. Which defect is not normally associated with TIG? Options: A, tungsten inclusion, B, crater pipe, C, spatters, D, lack of fusion. Think about the TIG process itself. The arc, the electrode. What's unique? Okay, the one that doesn't usually fit with TIG is C, spatters.
Yes, spatter. And this really points to one of TIG's defining characteristics, its cleanliness. See, TIG uses a non-consumable tungsten electrode. It doesn't melt, or at least it shouldn't. Unlike MIG-MAG or stick welding, where you have molten metal droplets flying across the arc. TIG doesn't really have that mechanism. The arc is smooth, stable, there's nothing really to splash around and cause spatter. Now, that doesn't mean TIG is perfect, of course. The other things listed, they can happen. Tungsten inclusion, yeah, if you dip the electrode into the pool by accident, a piece of tungsten breaks off. Crater pipe, we just talked about that insufficient slope out. Lack of fusion, sure, if your parameters are wrong or the joint isn't clean, that can happen with any process. But spatter, if you see significant spatter around a weld, it's a very strong sign you're probably not looking at a TIG weld.
Right. So for you as an inspector, seeing spatter is almost like a diagnostic clue straight away. It points you towards other processes like MIG or stick.
Exactly. It helps narrow down possibilities very quickly. It's understanding those fundamental process characteristics.
Which is precisely what the CSWIP exam tests. Okay, let's switch gears now. Let's talk about another very common process. In MAG CO2 welding, which parameter gives the greatest control of weld appearance during dip transfer or short-circuiting welding? Your choices: A, wire stick-out length, B, amperage.C, wire feed speed, inductance. Okay, this is specific to MAG using dip transfer or short-circuiting. What gives the best control over how the weld actually looks? The key parameter here is D, inductance.
Inductance. This one's interesting because it's often a bit misunderstood, but it's so critical for MAG, especially in dip transfer. So inductance basically controls the rate of current rise during that short circuit. When the wire dips into the pool, it shorts out. The current then ramps up really fast to burn the wire back. Inductance controls how fast that ramp up is.
Okay, like an electrical choke or something.
Yeah, kind of, yeah. Think of it like a damper on the current surge. So higher inductance slows down that current rise. It makes the arc softer. And the big benefit, it drastically reduces spatter. Dip transfer can be quite spattery, but more inductance smooths it out, gives you a nicer looking bead. Lower inductance means a faster current rise, a crisper or harsher arc. You might get a bit more drive, maybe slightly better penetration sometimes, but you almost always get more spatter and a rougher looking weld. So while stick out, amps, wire speed, they're all vital. Inductance is really the fine-tuning knob for controlling spatter and getting that smooth appearance in dip transfer.
That's really interesting. So an inspector looking at a MAG weld, especially one done with short-circuiting, if it looks like it's been attacked by, I don't know, angry popcorn with all the spatter, adjusting the inductance could potentially clean that right up.
Oh, absolutely. It can make a night and day difference to the amount of spatter and the overall bead appearance. Less cleanup needed too.
Okay, but what if a welder sets it too low? Maybe they think they need a harsher arc for penetration, but they overdo it. What does that look like on the weld bead itself? What are the signs for you?
Yeah, that happens. If the inductance is too low, the arc gets really harsh, very aggressive. You might hear it described as crackly or stiff, the biggest visual cue for an inspector. Excessive spatter, like you said, and not just a few bits, but everywhere, lots of it. The weld bead itself might look quite irregular, almost ropey, not smooth ripples, but coarse, uneven ones. You might also see inconsistent wetting at the edges, less smooth fusion. And ironically, all that spatter means energy is being wasted, so you might not even get the penetration you were hoping for. It's a clear sign the arc's not balanced.
Fascinating. How tweaking one electrical property changes the whole physical result. Right, last question for today. We're coming back to TIG, but focusing on the absolute basics, the electricity. What type of current is used for TIG welding of carbon steels? Your options again: A, DCEN, B, ACC, DCEPD, none of the above. Think basic electrical principles, common material. Carbon steel, what current do you need for TIG? And the answer is A, DCEN, direct current electrode negative.
Yes, DCEN. This is absolutely fundamental stuff. Every inspector has to know this cold. So DC, Direct current means the electricity flows one way. With DCEN, electrode negative, the tungsten electrode is hooked up to the negative terminal. What this does is focus most of the heat, maybe 2/3 of it, onto the workpiece, the metal you're welding. That's exactly what you want for carbon steel. Good heat input for good penetration, making a strong weld. And a side benefit is the electrode itself stays relatively cooler, which helps your tungsten last longer, doesn't burn away as fast. Now, just to compare, if you use DCEP electrode positive, most heat goes into the electrode. You get very shallow penetration, and you'd likely burn up your tungsten very quickly. It's usually for very specialized things. And AC, alternating current, that's the one we use mainly for aluminum and magnesium. That back and forth flow gives you a cleaning action to break up oxides, plus decent penetration. So for carbon steel TIG, it's almost always DCEN. Choosing the right current type is non-negotiable for a good weld.
Absolutely fundamental. Match the current to the material, get it wrong, and things go badly pretty quickly. So if you, as an inspector, saw a TIG weld on plain carbon steel, but it had really shallow penetration, or maybe the welder was complaining about burning through tungsten electrodes really fast, what current mistake would immediately spring to mind?
Well, the big giveaway would be that shallow penetration combined with electrode issues on carbon steel. That screams DCP electrode positive. They've got the polarity the wrong way around. The heat's going into the tungsten, not the job. You'd likely see the tungsten tip looking melted, maybe balled up instead of nice and sharp like it should be for DCEN. It's probably the most common electrical mistake for beginners on TIG with steel, just forgetting to set the machine to DCEN, or maybe leaving it on AC after doing an aluminum job. Understanding that link between current type, heat focus, and penetration is vital diagnostic knowledge.
Fantastic. Well, we've certainly covered a lot of ground today. We've looked at process selection for aluminum and mag. We dug into TIG controls like slope in, slope out, talked about defects like spatter or lack thereof, shifted to mag CO2 and the importance of inductance, and finished with fundamental current types like DCN for steel TIG. That's a lot of crucial info for CSWIP 3.1 prep.
It is. And notice how it all connects, right? Each detail feeds into the bigger picture of welding quality. For you as an inspector, mastering these nuances means you can assess welds much more effectively. You don't just see a defect, you start thinking about the why. Why did that happen? Was it the wrong setting, wrong technique? That kind of critical thinking is what makes a great inspector, both for the exam and, more importantly, on the job.
Couldn't agree more. So as you continue your journey, keep this question in mind. What really stands out to you about how these subtle choices, the process, the settings, the current, how they ultimately dictate everything about that final weld? Its strength, its appearance, its reliability. Keep digging into how these fundamentals underpin everything in welding. Understanding them deeply is truly your biggest asset. Thanks for diving deep with us today.